Any questions? Well, we last left off with the demonstrations, but I apologize because I hope none of you were crying yourselves to sleep last night because there wasn't enough math yesterday. So, yeah, I know, and I'm sorry.
Dave, you better make up for it.
All right, let's do that. We talked about forces between charges. You know there's a formula. Electric force between 2 point charges. So if I have a charge here, Q1, charge here, Q2. Then the force on charge 1 from 2. So this is the force on Q1 from Q2. It's going to look a lot like the generalized gravitational formula, except we'll just put that over to the side just to refresh your memories. F, the magnitude of the generalized gravitational force is big G, mass 1, mass 2 over r squared. It's going to have the similar type of format, except obviously it would have a different constant here because this is a gravitational constant, and gravitational constant doesn't really go in electric force formula. We use K sub C. I'll change that slightly in a moment. Times the charges over r squared, r2 hat. Now, similar to the gravitational field, or the gravitational force, if you imagine that you have a charge that's giving off something. Referred to it as gravitational pheromones before, we'll call it electric pheromones now. It is not a common term. If you talk to physicists and mention electrical pheromones, they'll have no idea what you're talking about. But charge 2 is giving off something that is shot out in every direction. And so the farther out this wave goes, the more spread out it is. And so since the surface area of a sphere is proportional to r squared, it makes some sense that we have r squared here. The fact that both charges have something to do with it makes sense, and then we need to have units, so that K sub C. Now, this K sub C here, this constant, has 2 names, and I will flip back and forth between them. There is Coulomb's constant, or the electrostatic constant. So I will either write it as K sub C or K sub E. And I haven't really settled upon what I'm going to sort of stick with for the rest of my life. And so I'll flip back and forth. Just recognize that if I say K sub C or K sub E, I'm referring to the constant up front. In terms of units, I know that the units of force would have to, if this is a true formula, would have to be the units of that constant times the units of charge squared over the units of distance squared. Let's stick with SI units. What's the SI unit for force? The SI unit for charge? see yesterday's notes.
Q. Newton per,
The simple unit,
oh, that's, C,
yes, which stands for,
Coulomb.
absolutely, times Coulomb squared, the SI unit for distance.
Meters.
So if I isolate K sub C, we find that the units for it are newtons, meters squared, or Coulomb squared, if we're dealing with SI units. And this is supposed to be a capital C here. Now, in terms of the number, on a calculator, it depends on how precise you want to be, but K sub C is approximately equal to the E, I'm on your calculators, most likely it's in the E button, it's the times 10 to the, so it's 9 times 10 to the 9th. If you want to go out a little bit further, 8.99 times 10 to the 9th Newton meters squared per Coulomb squared, and you can take it even farther if you wanted to. It would be all right, or, sorry, not a formula that I keep on the top of my head. More precisely, it is going to be for the speed of light squared times 4 pi times 10 to the negative 7th divided by 4 pi, where the speed of light is 299. I always have to look it up. Roughly 3 times 10 to the 8. And I don't have it written down on this page. All right. Speed of light is a set number. Yeah, that one's out. Questions up to here? Luis,
What are all the equations on the board?
the same as they were when I wrote them down.
Gotcha.
This is the formula for the electric force. But you can put a subscript E there just to make that more explicit. Formula for an electric force this would be the force on charge 1 from charge 2. This over here was looking at what are the units of this constant up front, which is either called the electrostatic constant or Coulomb's constant, depending upon my mood or your mood at the time. This is the quick and dirty value for that constant. This is slightly more precise. And if you look up the speed of light, you can actually plug it in here and get a more exact formula for the value.
Something.
Is that an E between the two nines?
Say it again,
An E between the two nines for the KC value?
louder please.
Is that an E between the two nines for the KC
Yes,
value?
that the reference to the calculator, that would be 9 times 10 to the 9th.
Sorry. Is that what E equals 1 over 4 pi k?
Here,
Yeah.
E, come on. It's an
Yeah, that's what I
epsilon.
said. It said E over 1/4 pi over k.
That's epsilon.
Epsilon.
Come on. Is equal to 1 over 4 pi k. Now that is, I use Coulomb's constant early on because it's just a whole lot easier than writing out a slightly more generalized formula. It turns out that there is another variable, another constant called epsilon. And I don't know. Epsilon or epsilon, depends on which form you prefer. I tend to write it this way. This is known as the permittivity of, actually, put a little zero there, of free space. Now, I'm going to mention some vocabulary that we have not covered yet. The electric force is theoretically caused by this thing called the electric field. The electric field will affect a medium that it is traveling through. There is a base value for this of how the medium is affected by it, and that would be free space. That is the bare minimum. And so this is how an electric field, or a measure of how an electric field affects the vacuum of space. That's what this is. So sometimes you will see this formula over there, since Coulomb's constant is also equal to 1 over 4 pi epsilon sub naught. So that formula over there, the electric force on charge 1 from charge 2 is equal to 1 over 4 pi epsilon sub naught Q1 Q2 over R squared. I just find writing the K easier than writing this. At some point, we will shift to this because this will become a more important concept to deal with. Questions? Yes, Laura?
I'm sorry, I'm late. Can you go over the, force equals G in 1 and 2 R squared?
That?
Yeah,
The generalized gravitational force.
right. That's from this.
What it's doing is showing that the parallel between this and
that.
this.
Okay.
Yes, Stephanie?
In your, well, I guess units, why does it have a 2 subscript?
Here?
Yeah.
All right, so this is the force on charge 1. If you recall, this is a radial unit vector. Unit vector, because I have the hat on it, radial unit vector means it is away from the center. The 2 here is telling me where the center is. So if Q1 and Q2 are the same sign, then the product is positive, which means that the force on 1 is some positive R2 hat, which means away from 2.
Okay.
So it's repelled.
Okay, thank you.
If they are opposite signs, it is negative, so I'll have a negative R2 hat, which means it's towards charge 2, if they're opposite signs. Other questions? All right, let's just do a quick plug and chug. It's as if this Sassen doesn't anticipate that I'm gonna be in here and then sets everything up to make it more convenient for me. What's up with that? Okay. As I've said before, if the world did not revolve around me, my parents would not have called me son. All right, so I have a 5 microcoulomb charge. That is so incredibly poorly written. Let's try that again. A 5 microcoulomb charge, and over here I have a negative 3 microcoulomb charge. Now, micro is a prefix that we will use quite a bit in here.
So are those 2 dots meant to be there?
Those two dots are the charges.
Could you? I'm not quite sure what you mean by that.
All right, when we had the Van der Graaf generator on yesterday, it was a sphere like that. It turns out that if you have a sphere of charge with a uniform charge distribution, then you can assume, you can treat it like it is a single dot at the center.
And is that like what we're conveying with that dot?
Yes.
Okay.
If I wanted to convey that we're dealing with not a point charge, then I would draw closer to the actual shape of the object. But that's the indicate, because the formula over there is actually the force between 2 point charges.
Thank you.
If we're dealing with a distribution of charge, then we either need to come up with some way of approximating it, which we will, or calculus, which, if there's big demand for it, we'll go ahead and do the calculus bit, but otherwise, from Luis's facial expression, I think it was sadness that we might not do calculus. Did I interpret that right?
Yeah.
Okay. Other questions? All right. Oh, I need a distance between them. I'm on using a 3 there. Should make that an 8 centimeters. By the way, the Van der Graaf generator, when it was charged up, it would have been, the charge on it would have been in the order of microcoulombs. All right. So, what is the force on the 5 from the 3? The electric force. Plug and chug. 9 times 10 to the 9th. Newton meter squared per coulomb squared. Times 5 micro? What is micro?
$1,000?
You said 1,000?
Yeah.
That's kilo.
Oh.
1,000th would be milli. I don't know if there's a name for that.
110,000?
Wrong direction.
Okay.
5 zeros.
Is it 1 -6?
0.00. I guess it would be 0.5 zeros then a 1, or 10 to the negative 6th.
Okay.
And if someone would be kind enough to pop that out on the calculator, or just pretend that I can do it in my head and go with whatever I come up with. In my head again, somewhere when we could easily do our calculator.
-21.1.
Negative 21 point. Thank you very much. All right. Wait a second, there's something off here. I'm assuming the math is correct. Anyone, I assume someone else got this? Or is there just all the faith in the world with Erica? And yes, I can learn.
I got, negative 1.6875.
Yeah, that's what I got.
Negative 1.6875.
Yes, sir.
Got the same as Erica.
Did you, the people got this, did you square that?
Oh, no,
I got the same as the top one.
hold on.
Then for those who didn't do it, you were right to have your face in. All right, so what's wrong with this answer?
It doesn't have a direction.
Because the negative is not really defined here. Now, if we determined an I-hat direction and figured out what that or a positive direction, that's fine, but there's nothing on here which indicates what the negative direction is. Now, intellectually, I think you know. What is the direction of the force acting on the 5 microcoulomb charge?
They're attracting, so
Spot on. Yep, they are being attracted to each other. So that negative is indicating that is to the right. However, it doesn't necessarily say that right here. So we need to somehow indicate that it is going that way. We can do it a couple different ways. Number one, I could just do the R2 hat. And that indicates it's in the negative R2 hat direction. In other words, it's towards R2. That's perfectly fine. Or we could have established that, well, let's say to the right is positive, in which case the answer would be 21.1 newtons. We could have said to the right is the I-hat direction, and make it 21.1 newtons I-hat. So there are different ways of expressing the exact same answer. Probably the simplest is doing this.
So if the answer was positive, it would indicate it's,
Yes.
go to the left, then it would be R hat 1.
No, it'd still be R hat 2, but it'd be positive R hat 2, which means away.
Okay.
If you're having trouble recalling that when we did the radial unit vectors, we would have probably first hit it in chapter 6, the centripetal motion.